Right. The floor is yours. Yeah. Thank you very much for being with us here today.
I want to first of all thank you all for being in the room and thank the organizers for inviting me. I'm having all the FOMO for not being there. I'm sure this has been, or this promises to be a wonderful day, and it's hard to follow up, Thomas, with such a great talk. Okay, I'll try. So I'm here to talk about object-oriented and causal representations, which I really start to think of them as priors, and in particular in the context of autonomy and robotics or embodied autonomy, I think of them as abstractions. You don't always need these priors at the lowest level, but you can have priors at different levels of abstraction. And of course, ideally, we want to learn them, as the theme of this workshop is, in a manner that is nearly unsupervised. And that is what we'll gun for. So as a very broad set, as an introduction of myself, primarily I work on reasoning and control for embodied learning. And to that end, we take the approach of building structured representations and causal discovery towards these processes. And what I'm going to do today is to give you a snapshot into some of the projects we have been doing the last 2 or 3 years, following this idea. And of course, some of these ideas have flowered in the community really at scale. So first of all, a lot of people talk to me about why priors, why biases. I like to think about this slightly more open-ended in the sense that whether we start in the history of machine learning, going all the way back when it was still philosophy and psychology, people have always argued, and this is an excerpt from Tom Mitchell's book in machine learning, that to make any inductive leap necessary to classify instances beyond the observed, we need other sources of information, or you can call this biases, to choose one solution from the other, which is basically saying that you will need inductive biases to create particular kinds of solutions that work. A general purpose, like a general purpose architecture, may not be super simple in that sense. Of course, it may be elegant after the fact. One statement of this idea is basically there is no generalization without no notion of structure, but structure itself may be many things. So one could argue that to get autonomy or generalization, you'll need 2 things. You'll need some mechanisms of getting data. Data itself can be many flavors, and we are not going to talk about that today. But we'll talk about structure. Structure can be domain knowledge, inductive bias, symmetries, priors, and this whole idea of object-centric and causal representations is effectively, according to me, a notion of structure in this setup. So today's talk, I want to focus on agents. I don't want to. I think Thomas already did a very good overview of building representations that are object-centric over the last few years, particularly using slots. So now what I want to talk about is to talk about, first of all, how to do these things, how to use these information for decision-making, and in particular for decision-making, what sort of problems we are interested in. So the first way to really think about this before we get into object-centric or causal representation is in the setup of decision-making. Let's say we are going to take the MDP view of the decision-making. This is not the only worldview, but let's say this is one viewpoint. One of the problems is we need to define an environment which tells us that what is a reward function, or what is the task that you need to complete. You're opening a door, the door needs to tell you it's open. Right now, when you really think about this, that is where it's all of the black magic, or in robotics is. Reward engineering is where a lot of the hand-designed features go. Right? It's delayed. It's basically doing feedback control with trial and error. And that is the problem we want to solve, according to me. So first of all, my argument is that task specification should be very much independent of the solution. What that means is... we borrow ideas from our friends in neuroscience and cognitive sciences, where they call this idea called prospection, which basically says that we do action generation, which is movement, as a consequence of what we can call a covert internal simulation. So simulation and generation of movements are effectively sharing the same computational basis. And you're dividing the problem in a simple sense in the what and how. So let me just sort of ground this idea. If you're trying to open the door, you can imagine how or what opening a door looks like, and then figure out how you, with the constraints you might have, will achieve this goal or will achieve this change in the environment. So in a sense, you can think of this world as two problems, a what problem and a how problem. The what problem can effectively be a generative model, which is learning to predict effect of some actions, right? So it can be how to open a door, open a jar, or if you're not given an entity, you're basically saying open an image. And you ideally want this model to be compositional, counterfactual. You want to ensure that it preserves multi-step semantic consistency. And even better, it is pre-trainable over a large problem setting. This is what, so that we can effectively build a foundation model. Now, once you have such a model, you can use this model effectively as a goal generator that you can use for a goal condition reactive controller. So if you're trying to open, let's say, the oven, you can solve this problem online or offline for a variety of different agents. The concept of opening the oven does not change whether you open it with a humanoid robot or with a human, or a child does it or a dog does it, right? So there is this separability of what needs to happen and how it needs to be done. So this is what I would like to preach or pitch here, that we should start thinking in terms of structure of the what and how, and we can build pre-trained models, large-scale priors for both of these problems simultaneously and separately. Okay, so let's talk about, first of all, what this prediction model might look like. So this is a problem we have been working on for a while, and the whole idea is fairly simple in the sense the requirements are simple, that you want a model to be self-supervised. Ideally, it should be modular representations of objects. You want to preserve semantic consistency, and you do not get any sort of supervision during training. So you do not get bounding boxes, or you do not get object-level supervision. You might get partial supervision through language instruction, and this is something that we were working on back in 2020, 2021. So this was a paper 2 years ago at CUPR, where we call this idea modular action concepts. The model was trained purely with a slot-style architecture for discovering objects, and it can take in language input. So let's say take jug, open fridge, put jug in fridge. But nowhere during the training data do we provide any sort of let's say object-centric representations or feedback. So effectively, it's videos and language that you train with. And this is, of course, a much smaller scale model than the current video prediction models are trained with. However, this is one of those precursors where we are very interested in taking this idea of training a model on a fixed data set, and then also trying out what I would call a counterfactual. So you can basically say, for the same initial state, what if I change the instruction, and can I do something like that? It's important to note that this model is conditionable with arbitrary initial states, and then you go forward in time using language as the actions, right? And the important thing about this result at the time was to ensure that it could maintain semantic consistency, especially compared to prediction models at the time, which were not really object-centric. So because there was no notion of objectness, over time when you do predictions, you might lose some objects, or you might create copies of some objects. So this was pretty interesting, right? Now, of course, this idea was very good, but limited in terms of scaling. And this is where I think that we were also simultaneously looking at this idea that, okay, what if we only have videos, we do not have language? What can we learn with these sort of systems? And this is where the idea of slots also comes in. Thomas already gave a very good overview of what slots might look like. In these cases, you start with images, and ideally, with the reconstruction loss only, you want to learn a latent representation that is disentangled. Ideally, these disentangled representations are object representations, right? So if you do it correctly, you might end up with different representations for background and each of the independent objects. And of course, there is an implicit assumption here that the data is of the right type for you to be able to represent independent objects correctly, which means that you've actually seen different variabilities of the data taken from a pure causal perspective, right? And then this idea, of course, can be done frame by frame. So the work we did with Thomas actually and Z.E. Wu, who might be in the room, I don't get to see him. We took this idea of learning slots and we applied a representation model for prediction using transformer architectures and using only causal reconstruction or a causal model for prediction to do recurrent reconstruction or autoregressive reconstruction. And this actually already enabled us to do much more than was possible last year, which was we can now build in these video prediction models and not only build these video prediction models that are consistent, but also reasonably high quality. And you could use them for a variety of tasks downstream, whether question answering or decision making. Did you have a question? Okay. I don't think I can hear this.
Just chatter in the background.
Sure. Okay.
So there is no question, just chatter in the background. So you just go on.
Oh, okay, got it. Sorry. Okay. So then, of course, we started with the idea that we extended the slot former idea, and Z was able to build in a diffusion decoder, which allowed us to do a little more. First of all, we were able to take this idea of slot-based object reconstructions to more realistic objects, more complex scenes, which have higher quality textures and visual fidelity. And again, we preserve the disentanglement courtesy of the slot representation, but this time around using diffusion models. And then, of course, we have taken this idea slightly further this year, actually, to build what we call ego sim. This time around, we basically understood that representation of scenes can be not only object-centric, but also separable in ego movement. So what you see, motion in the scene because of ego movement versus motion in the scene because something in the scene is moving, should be separable, and separable in the representation itself, in the architecture. So in doing so, we can now do very precise camera control while predicting precise interactions with the world in a separate setting. So overall, what I would argue with these sort of lines of work, we were able to study different aspects of object-centric representations and also then build on these object-centric representations to build world models. Of course, our world models are much more modest compared to the latest models that people are building, but we still believe that the architectural advancements or the insights we are building are very useful for people who will be training the next generation of large-scale video foundation models. Okay. So far I talked about, okay, we can build some version of a video prediction model that will tell us what to do. But still, how to do it is important, meaning, okay, we have a video prediction model. What can we do now? First question we should really think about is, even if someone tells you that you don't need to open the door, you need to figure out how to open the door. And this is the line of work we have been working on, which is, yet again, the same idea that you want to learn to interact with objects in an object-centric manner without the need for supervision. So let's take this as an example. This is an object. And if I were to show this to you and say, okay, what are the possible modes of interaction, or what can you do with this object? And most of the people in the room might say that each of these objects might have a separate motion. Maybe there are 6 of these independent entities, and each of them move in 2 directions, right? And of course, we want to take this idea and generalize this to all sorts of objects, whether it's drawers, doors, faucets, and all sorts of stuff. But we want to do this in a manner that is not using any sort of privileged information, right? So during training, we don't assume segmentation. We don't assume access to ground truth models. We operate with only visual information, in this case, RGBD or depth, right? So in principle, this method can be applied in an online fashion to the real world. So now what do? We think of this problem as a 2-phase problem. There's a play phase, which is kind of data collection, and then there's a model training phase, which predicts these models. So the play phase is effectively equivalent to doing contrastive learning, where you interact with the world without representations here. But you're basically saying that I did some action, and the action resulted in a change in the world. And I want to figure out if this change is semantically meaningful. So you are effectively clustering the chain and then doing a joint embedding with actions. So now what that results in is effectively you learn, this is only for informational perspectives, that you might have many possible actions, but many of those actions result in the same change, and that same change can be effectively treated as a mode of interaction. So there are many ways to push the door closing, but effectively it's the same action, right? You can sample an action and you can have many ways to do the same thing, right? And doing this iteratively ensures that you not only discover, let's say, the more frequent modes, but you are able to make sure that you discover rare ways of interacting with the world as well. And now once you have that, you can basically train an encoder-decoder style architecture, where this time around the output is an action. So looking at an image, maybe a text input or an image input for the goal is provided. And you can basically say, what are the things we can do? And if there is no conditioning provided, you can do sampling in an unconditional manner, which would basically give you modes. So you'll basically be sampling from one of the modes, and each mode will result in something meaningful, right? So what that results in, now we have a system which learns purely unsupervised, a system that can interact with objects in a purely unsupervised manner without the need for any behavior cloning data or any data about the assets themselves, right? And you can take this system to do goal reaching. Of course, you can take this to say, okay, now close or open the same object. Notice there is no conditioning on language in this case, or grounding with language would be fairly easy. And then you can, of course, do something more where instead of just doing single view input to make robotics viable, you can have a multi-view transformer which can take multiple views as input, simultaneously do fusion, and then do this prediction. So same idea. And then you effectively result, again, in a very open-ended setup where you can provide it any sort of let's say object, and it needs to predict where to interact with the object and what that interaction would look like. It is important to note that it's completely unsupervised and it's completely, let's say, object-centric. And from a pure perspective of like just results, we were interested in seeing, okay, how does this work in terms of discovering meaningful and successful modes of interaction, which means that it might discover many modes of interaction, but how many of them actually result in meaningful outcome? And based on a variety of papers that we compared with, we found that we get to over half of our interactions that we learn are actually resulting in meaningful, let's say, change in the environment. And when I use the word meaningful, it means salience that can be grounded in language. Interestingly, if you learn such priors, you can also use these priors directly in RL. So someone tells you to open the door. Maybe you don't know what the concept of opening is. Maybe you have a diffusion model which tells you as a classifier, is the door open or not? But you know that the door should only be interacted in a discrete and a small number of ways. And in doing so, exploration becomes very fast. So if you look at the curve on the left, you see that these methods which have priors work to get to some level of performance very quickly. And I'm not even showing RL because it would not even show at the same scale of time. So building priors really helps in what I would call enabling the right representations that are about the objects. So you know how the world works in a sense, especially how you can change the world. And then using these priors can either be grounded in language that enables you to interact with them in a chat style interface, or you can also use these priors purely as, let's say, policy priors for reinforcement learning for goals that you may not yet know, right? So now we talked about this idea that, okay, we can do priors for objects, but we can also do priors for actions. So think about actions in the world, whether you are pouring something or you are opening a water bottle or you're doing some of these actions. Often the notion of actions has a prior over the set of objects, not just a single object. So if you think of an object that is being poured, you can really start thinking about, okay, pouring, despite the fact that there's so many different types and settings, has a very simple common functional form, right? You can say that there's an object that you pour from, there will be a region that you pour out of, and then there will be a region that will pour into in the receptacle. This sort of templated representation actually is very interesting because you're now not thinking of poses of objects, you're thinking of the whole scene or all of the objects in a single representation. And in doing so, you are basically learning what I would call effectively action concepts. So you're learning that pour from mug to bowl doesn't really depend on the shape of the mug. It really depends on the fact that there will be a region in the mug that the stuff will come out of, and then there will be a region on the bowl that the stuff will go into. As long as they are aligned, we are good to go. It basically gives you a kind of generalization that would otherwise not be possible explicitly. And because these things are trained in simulation with depth images, you can actually put them on the real robot, and you don't, again, need to have the exact same object categories. So you can have novel categories to put into. Notice the policy here is very simple. The policy is just aligning the right parts. What you're really doing in an unsupervised manner is discovering functional parts on the object. Right? So now we talked about parts, right? Part discovery is something that has still eluded folks. So because the notion of parts is still very hard, even the latest and the best foundation models don't really do well on part level understanding. They can do at object level understanding, but part discovery is still very tricky. So in the previous one, we talked about this idea that, hey, you can have parts, and not all parts may be the kind of parts you might think. You might not have a cup which is labeled as rim, but you can still discover those regions on the object. Now, what we are talking about is if you have such regions, what can you do with them? Well, you can do very interesting stuff. But to do interesting tasks, often you have to grab and interact with objects in very particular ways. Of course, with human hands, these things are, let's say, supervisable through data, but with robots, they may not be. So we've built this kind of architecture where you can have very open-ended kind of setup. So you can pick up the water bottle with a power grasp. What that means is the power grasp effectively means that all fingers and palm should be on the body of the bottle. But now we need to understand what is the body of the bottle. And where, in this particular case, we can now have a diffusion model that is basically trained to predict a particular type of grasp candidate on relative parts of the object. And then you can use differentiable simulation, and I'm not going to go into details of some of these things, to refine that model to result in a particular solution that achieves the goal. So in this case, you can say cut papers. So you're not saying where to grasp the object. It's basically saying if the object is being grasped in a functionally correct way, you can do this, right? So loosen the cap means that you need to grasp the object in a way that would allow you to loosen the cap. And of course, because this model is fairly generic, you get both multimodality in the sense that same object can be grasped in different ways, but also category level generalization where different dispensers may have different shapes, but really the cap is what we care about. Right? Okay, so I think so far I've talked about this. I think I have maybe 5 more minutes left. So now I want to talk about something else. So far we talked about this whole idea of object-centric representations, but what about causality? So far, we talked about skills. You can interact with objects, you can open things, you can close things, but these are small skills and they are very valuable, of course, as priors. But a lot of the things real robots will need to do will need to be more, right? Will need to be the structure of the world that might be maybe open the door, make breakfast, so on and so forth. So now the real question is, what can we do about learning the structure of the world? And what should the structure of the world be? Like when we think about world model learning. So this is where I'm talking about this idea of causal reward models, where we use a very sparse representation of the world to build a structured representation that enables faster exploration. And I'll explain how. So let's think of a very simple example. Maybe someone says how to make a French omelet. You might say there are sequence to achieving this task, right? So now someone might give you instruction, but the instruction is at a very high level, right? So add eggs and half. They didn't tell you how to do any of the details, but they told you that that's step one. If you achieve step one, then you can carry on to step two, and so on and so forth. And this really solves a problem in RL, because often problem in RL for these long horizon tasks would be, how do I build a reward model for something like this to even begin with? And then how do I handle conflicting objectives? And even more so, how do I handle non-linear sequences? So maybe when you say add eggs and half, does it matter if you add eggs first or half and half first? In principle, one could argue no, right? So this is the problem we are out to solve. And we argue that you can think of these things as achievements. Each of these tasks or each of these sub-goals can be thought of as achievements. And within that achievements, you are basically initializing a causal graph, or a graph per se, a DAG very specifically. So this sort of achievement structure is kind of true for a variety of things in practical settings, including, of course, games. So whether you are making omelets and whether you chop onions first or tomatoes first doesn't really matter. They are interchangeable, but you cannot move to step two because they are both preconditions for the next step. Maybe mix them and then add eggs. And this kind of structure, of course, exists in many games. This one particular example is Crafter, which is a simplified game where you have to do image to control style policies, and it has many sequences and a multi-layer deep architecture. So in this case, what happens was, if you take this model and the way it is structured is that if you use reinforcement learning without the knowledge of background infrastructure, the best models basically get you 5 to 10% of success. And usually this is just early stage tasks and it doesn't really get very deep. So what we presented is this idea that you can build this model of achievement. So you can collect data with agents, and then you can learn in an autonomous manner or completely unsupervised manner what are achievements, meaning what are these sequence of goals that we should learn. You can then learn a graph over these achievements, which is effectively, you can think of it as you're learning a latent MDP, and this is the dynamics model of that model, a graph, or you can also interpret this as a causal reward model. And once you have this causal reward model, you can do exploration much more efficiently. And of course, this process can be iterated as well. So just as an example, for the same thing that I was showing you, which was a 22 level sort of deep setup, we found that our model can find a graph structure based on agents that were not necessarily, let's say, perfect agents. Even then, our recovered graph is very close to ground truth. Notice that it does make some mistakes and it misses some edges, and it also invents some spurious edges. The dotted edges are the ones that are the differences between the two graphs. But regardless, we find that the structure that we discover is very, very similar to the real world. And in this case, now if you use the structure, of course, you can do much better exploration because you know what the goal you should be even attempting to achieve given the current context rather than doing random things. Of course, it improves performance of our RL agent. So now we can achieve 60 or to 80% of the tasks, while almost all comparative models are less than half. But the most important thing we found was baselines were able to solve easy tasks. So they were able to get far, not very far, but they were very efficient in easy tasks. But they almost flat out failed when exploration became ever so slightly harder. So collect diamond was like the hardest task in the setup, and none of the baselines ever achieved anything at all. And our model, even though it's trained on agents that are effectively suboptimal, still gets very far. So the takeaway here would be that really semi-sparse and semi-informative reward models like achievements are very easy for designers to specify. So I can tell you, or maybe a large foundation model can tell us, if I'm trying to opening a door, I can tell you, is the door locked or unlocked, or is the door open or not, as classifiers. But providing them as dense reward models for agents to follow is much harder. And our model automatically divides the environment into smaller subtasks and then learns this invariant reward structure as a DAG that you can allow it to use in multitask environments. So towards the end, I think I want to recap. If there's only one thing that you take away from this talk, please let it be this: that the idea of separating the what and the how is very powerful. It allows us to start thinking in terms of scalable architectures and models. I can build pre-trained models of what needs to happen in the world, what is the concept of actions. And these actions can be at the levels of abstractions. These are priors. And separately, the how model, which is how would a robot achieve a task or how would an agent achieve a task, can also be a separate prior, but at a much more granular level. Think of an agent learning to do many different tasks: open a door, crack an egg, or mix an egg, while the what model can tell you what the high-level recipe might be. And using this separation allows us to build large-scale pre-trained models and really use as much data as we have on available to us to build very robust models and then combine them after the fact at test time. Of course, sometimes that combination may need planning, but we can go very far with this perspective of building large-scale models. These are some of the papers that I got to talk about. A lot of the work is done by excellent students. ZE might be in the room. Lichuan did a lot of the work on representation learning for skills. Wei Yu is leading the work on part-based manipulation, and Wei is leading the work on building video models with camera control. With that, I would like to thank you all for being such a patient audience, and thanks a lot for the privilege of your time.
Thank you very much.
Thanks very much for your very interesting talk. At least I have some very new pointers for my own research. I don't know if you can see me.
I think I can, yeah.
Are there any questions from the audience?
We go to the second slide.
Can we go to the second slide?
Oh, second slide. Was it this one or or the one after this one?
We just see your front. Yeah. Oh.
Yeah, it was this one.
Yeah, this one.
Okay.
I guess. This one.
No,
The previous one.
Previous one. Okay, sir.
There's a lag.
Oh, I'm so sorry.
Oh, here. Is there a question or a...
No, just
Okay.
Oh man.
It would be if you could share your slides after.
I will share my slides as a PDF. Happy to share that. So we don't need to do this. If there's a question, happy to do questions.
I got a question. Okay, you present a lot of interesting, very interesting works. So in particular, what caught my attention was self-supervised learning of way of interacting with the environment, like learning how to open the drawer without any like privileged information, as you mentioned. But it was not clear to me whether you have to rely on a simulator, like do you? Because that is, in a way, it's from a computer vision perspective, that's actually very privileged information. Like you don't really get the simulator for the world. So I just wonder.
Algorithmically, no. The algorithm is completely structured in a way that there is nothing in this system which requires a simulator. That was, in fact, one of the axioms of the project, where we will not use any information, only observations that you will get on a real robot are required. That said, the data requirements were such, at least currently, that doing this on the real robot will require of the order of like tens of hours of interaction for it to completely learn from scratch. But this wouldn't be completely completely surprising, because one could argue like a child still needs days of interactions to learn these sort of things. So the scale of data required on the real world would still be non-trivial. I wouldn't say not achievable, but non-trivial for sure. But there's nothing in the algorithm currently that requires the simulator. Simulator is only a data generator for us, actually.
So if if this robot, I mean, I completely believe you, but if you had this robot in a, in an environment in the wild, where everything is not super clean and everything, how well does it generalize? Like, so
Yes,
I completely understand the point of a simulator, but my
yes.
question is generalization.
Yes, we are working on this, evaluating exactly this. So one of the things we did in the simulator was the scenes were single object scenes. I wouldn't say single object in the sense that like you might have objects which might have parts, but this is still a single entity scene. So we are not, and in the real world, when we are implementing this, we are using, let's say, pre-trained models which can tell us at least a big picture sort of segmentation of the scene. There are gaps. The gaps would be in the kind of, let's say, sensor gap, basically, because we are using RGBD input from simulation. RGBD from real world can have sensor noise. So that needs to be handled. I don't have a particularly satisfying answer right now, yes or no. All I want to say is currently the architecture, the way it is set up, it does not use anything about the simulator. That said, I'm not saying that if I go to the real world, it will work as is, but it would be more of a data collection problem rather than an architectural change problem.
Right. Well, thank you very much. Oh, there are now many questions. In the interest of time, let's pick two. Yeah.
Can hear me, or you will translate?
I'll repeat if he doesn't.
So regarding that slide that you shared, right, that the repeated the second slide, in that the final stage was transfer and safety. So my question is, all these models that we are building, how is the safety part being incorporated? Like certain times, certain trajectories will be simulated that will violate certain safety constraints. So are these models already built incorporating those actuator limitation or certain safety norms that will be in the real robot, or that is like the
right? I guess you heard the question, or because
that's a wonderful question, first of all, and a lot of practitioners in robotics are definitely thinking about this. I think it's an open area. First of all, when I use the word transfer and safety, there are two problems. Transfer is more generalization problem, which is like you may or may not have seen the instance or the scene or so on and so forth, or the dynamics may be different. And then the safety is more, will you be able to do what you expect you'll be able to do? And both of those problems remain open. We and others in the community, both in robotics and machine learning, have worked on these problems. But I don't think there is a general one-stop shop solution for these methods. You can, of course, build safety during both training and deployment. But because these are RL/machine learning models, a lot of them are supervised learning models. We have the same challenge as would be the case in deploying any of the supervised learning models, where generalization cannot be predicted ahead of time. You can only have probabilistic guarantees.
Thank you. And one more question. There was, yeah, one. Yes.
Okay. Yeah. Just about the grid talk, by the way. Just about the last one, the crafter with the crafter environment. I understood the general idea of creating these achievements as sort of self-directed reward functions that you design. But then So where do these come from? How do you generate them? And then how do you string everything together into a dependency graph? Because the part was.
Oh, sure. I should say this. So what happens is, think of them as, so you use data. So there are agents which can provide data for, let's say, parts of the graph. There may not be a single agent that does everything all at once, but you have agents that provide data, and the data may not be complete end to end. So think of it like this as, in this particular crafter environment, these are game trajectories, but you have a lot of these trajectories, which are snippets between let's say episodes to episodes or achievements to achievements. Now, first of all, you need to basically do clustering of common achievements in a state space. So you're basically saying that what you're learning in stage one is what states constitute an achievement. So for example, in Crafter, just to show you, collect wood. When you collect wood, your inventory of wood goes up by 1, right? So when you look at that context, you should basically know that this trajectory or this snippet resulted in a particular node called collect wood. We, of course, don't have the grounding of collect wood, but we identify that this is a node in the graph. So this is basically node identification. Once you have the nodes, then you can basically go back and connect them into a graph. In this particular case, because we have trajectories, connecting them into a graph is actually easy. We don't need to learn that in a sense. And then once you have the graph, then you can basically use the graph for sub-policy learning. So at any given state, you basically propose a next target, and then you learn the controller to get to the next target, irrespective of what you might need to do beyond that. So you basically break down this problem, this large MDP, into where every edge is a separate MDP.